What we did, I defined orthogonal polynomials, and essentially these orthogonal polynomials are useful because in terms of them we can express average density of levels, density correlation function, and a remarkable identity is that we don't have to sum over orthogonal polynomials of all orders up to very high one, because different terms here cancel out, and what we have only the boundary term at n and n minus 1. So it is still not easy to find any asymptotics of orthogonal polynomials or the corresponding wave functions for large quantum number, but it is at least one difficulty of summation is not present. So then I told you that the main ingredient of the Wigner-Dyson theory is so-called correlation kernel, and in terms of this correlation kernel we can express the average density, we can express the density correlation function, and we also can express multiple point correlation functions. So the task is to find an asymptotic form of the wave function, and the wave function is the product of orthogonal polynomial and the wave function which depends on the confinement potential, and I told you that there are classical polynomials which obey a certain Schrödinger equation, and there are non-classical polynomials where such equation of the second order does not exist, and then one has to apply a general procedure by computing moments, by computing Gram-Schmidt determinant, and then eventually in terms of this determinant one can compute the orthogonal polynomials, and also three-term relationship which follows from this structure. This is a more difficult situation, and therefore arbitrary confinement potential, especially confinement potential with shallow confinement, is a mathematical problem quite challenging, and it is now being developed somehow. But if there is the Schrödinger equation, then it is easy to find an asymptotic form of the wave function at large quantum number. And to do that, this is how this wave function looks like for the harmonic potential. So in the middle for energies close to the maximum density, it is sine or cosine. It is so one has to if you go towards edges, then of course there is a deviation from the sine and cosine, and you know the appropriate theory. This I have shown to you. This is what how semicircle looks like for finite n. So there are some solutions here, and this is a new picture which I did not show you last time. This is I computed for you the correlation function, this one, the correlation function in terms of the kernel, which is product this by that and minus this by this for beta equal to. And I computed it for you with the known Hermite polynomials and all these things. It is just the illustration. So you see what happens. What happens is that there is level repulsion. So at zero frequency, you have what is called a correlation hole. This is the level repulsion. And then there are oscillations with a period equal to mean level spacing. And for beta equal to, these correlations are remarkable because at some points they are exactly zero and they never cross unity. So they approach unity as it should be, because this unity is simply when the correlation function is decoupled, and then the numerator and denominator cancel out, and at large energy difference, one expects such a decoupling in a normal case, and this is what happens. But now what I want to just show you, this is not very big n, the matrix is 50, and this is 200. And what we see that qualitatively this is everything the same, but you may notice that here there is some difference between the even pulse and the odd pulse. So this one is deep, this one is not so deep, then again it is deep. And here there is nothing like that. There is simply a regular decrease of the minimum. So this is, I will show you later that this is the form that one can get in the limit n to infinity, and these are deviations. So it's just the illustration how the exact form may depend, may be different from the limiting one.
Sorry, can I get back? So why these points appear where on the scale of like mean level spacing where it goes exactly at 1? Why these peaks appear?
Why it is exactly one and never crossed?
Yeah.
Look, this is something which
I mean,
which has to do with analogy with non-interacting collectors. So we will see a bit later that for non-interacting collectors it should be like this.
Okay.
But if they are interacting, then this is not the case. They can cross.
Okay.
Okay. So so now I just recall you. So my goal now is to use this orthogonal polynomial stuff in order to calculate the correlation kernel. Because if I know this correlation kernel, I know everything. So I will now concentrate at mostly at the case where the confinement potential is quadratic, but here I just remind you what is Wenzel-Kramer-Bühler approximation, so-called quasi-classical approximation. This is basically from Landau-Lifshitz. So if you have a Schrödinger equation, it can be rewritten in this way, and then it is useful to look for a solution in such a form. So instead of phi, you are, of course, this sigma depends on it. So you are looking for the solution for sigma. So when you plug it into here, you will get an equation like this. So it is a nonlinear equation, so in general it is difficult to solve it. But what one can do, one can do the following. One can formally expand the solution in terms of a Planck constant here, and so to have the first zero order in Planck's constant, first order, second order, and so for that you just substitute this thing into here or into here, and then you sort out terms separately, terms of the first order, terms of the second order, and so on. If I neglect all these higher terms, then what I can get, if I neglect this term, so I will get this simple approximation, which tells you that it is essentially the coordinate dependent momentum. So if I would have just no potential, then I would have just IPX and then the momentum would be a constant. So I think I'm sorry, I have missed here the linear, sorry, yes, sigma is momentum, so there should be also x here. And so that if the momentum is constant, then there should be, the potential is constant, then the momentum should be constant, and the form of wave function should be IP, which is constant times x, so x is missing here. Okay, so so this is when it is possible to introduce such local momentum. It is possible to introduce such local momentum when the potential varies slowly and the energy is large. So then it is not that potential should be small. It is not necessary. What is necessary that it is slowly varying. So when it is slowly varying, you can say, well, adiabatically I can take the coordinate dependent momentum and be happy with that. So, you know, if you compute the second correction, so you plug this into here and then collect terms which are proportional to each square, then you will get the next correction, which is sigma 1, and this sigma 1 obeys the equation that sigma, the derivative of sigma 1 is the second derivative of sigma naught divided by first derivative of sigma naught. Since we know and denote this sigma naught like p, then sorry, I think I was not very careful yesterday. So P, I think what one has to do, one has to, okay, so let us leave it as it is. But here is the everything was correct here, because this is the derivative of sigma naught. Momentum is the derivative of sigma naught, and sigma naught you should integrate it, and x appears here. The derivative of sigma naught, the first derivative, is coordinate dependent momentum. But the second derivative of sigma naught will be derivative of the momentum. And then the first derivative is here, and so what I get p prime by p, it is the derivative of log. And therefore this sigma 1 is like this, it is log p plus some constant. And now what I can do, I can compare sigma naught and sigma 1. And if sigma 1 is smaller together with this factor, if it is smaller than sigma naught, then approximation works. If it is not smaller, then the entire expansion has no meaning, because if this term is larger than that, we don't expect that all others will be smaller than this. If we compare sigma 1 together with that, with sigma naught, so we will arrive at such condition of applicability. And if this condition is fulfilled, then this term is smaller than that, and we can trust this approximation. But what is important that if you remember in our wave equation, Schrödinger equation, there was nothing like h bar. So here the h bar is only the parameter that allows to sort out all these terms and correctly write an first approximation, second, and so on. But in fact, the condition is this. And if I set h bar equal to 1 here, and this condition is fulfilled, so then everything is okay. So I don't have to keep to consider h bar small. I can set it 1 and do what I did before, provided that this condition is okay. And then, sorry, not 0, but 1. And then this equation will be rewritten in this form, and this tells you that the condition of applicability, even at h equal to 1, is when the derivative of the potential is small, or the momentum is large, and the momentum is large where the energy is large. So, so this is why this is a good approximation when the momentum varies slowly, and the energy, and we consider the large number n where energy is large. Anyway, this is the formal approximation. So now I can collect sigma naught and sigma 1 and then if I keep only these two, I have the following form of the solution of the Schrödinger equation, and there are two solutions, one with sign plus, the other with sign minus, because this derivative there is square here. When you resolve it, there will be two possible solutions. So now what we know that if the potential is even, like we consider most of the time, then and there is one-dimensional situation, then the wave function is also real, can be made real by a proper combining of these two solutions, and the even at even n it is a cosine, and at odd n it is sine. So basically the combination such that at even n there will be cosine, and at odd n there will be sine. But then of course this factor is also taken into account, and in principle every wave function is determined up to a constant of normalization, and this normalization should correspond to the one in Hermite polynomials. What also is following from Hermite polynomials and cannot be found from this semi-classical approximation is this constant, as I said. In particular, there is a sign in this constant, and to find the correct sign, one has to return back to the definition of orthogonal polynomials like this, and then one can see that at x equal to 0, the sign is alternating. So, for instance, the zero order polynomial sign is plus. For the second order polynomial, the sign is minus, and so on. So it is alternating. This, of course, has nothing to do with semi-classical approximation. It has to do only with this three-term relationship. And then, if I take this into account, then I have the correct signs here. So now, having this wave function, I can plug it into this formula, and you see what will happen. As I said, one of these is sine and the other is cosine, and here vice versa. The first one is the first one, the one which depends on x, will be cosine, and the second one will be sine. So, you know, sine times cosine minus vice versa, it is a sign of the difference. And so I have the sign of the difference, and here I have the difference. So, okay. What I want to do, I want to compute this correlation kernel when x and y are small compared to the size of the semicircle. So the size of the semicircle is square root of n. So, and I want to compute the correlation kernel in the limit when n is large. And when n is large, then I can, to the first approximation, neglect, consider that x and y are much smaller than the size of a semicircle, and then let us take this formula and plug it here p at large n. And so if I look at this p, if I look at this p, I see that it is square root of 2 energy minus something that is dependent on x, for instance, simply x squared. And if this x squared is small, so what remains is the square root of 2 energy. And now I use the fact that it was a quadratic potential. Then the energy we know. It is harmonic oscillator. And then when I put this energy in the definition of P, I will get P like this, and the integral of P, which is in the exponent, the integral of P here, there will be simply x times this factor. And now I do this business sine times cosine minus vice versa, and what I will get sine of the difference.
Sorry, why do we neglect the potential term? Because n is large. So we consider
N is
large, and there it is like its energy
No,
is
no,
way bigger than
n is large.
Okay.
I'm going to obtain the asymptotic form of the wave function when n is large.
Yeah, I mean like you neglected the v of x in the definition of p, right?
Sorry?
You neglected
I neglect v
Yes,
in
the
under the
definition,
square root.
Okay.
And I neglect 1/2.
Yes, obviously. Okay.
Okay, so I will get such a form. And then what remains for me to do is only to determine this normalization constant. And in order to determine this normalization constant, so one can do it in a more regular way, but for me, the simple thing is that I know that if I take this kernel at coincident point, it will be the density close to the center of semicircle, and this solution for the density we know from the plasma model, and this solution is 2n minus v of x divided by pi rho of x, and when I neglect this thing compared to n, so I will get square root of 2n by pi. And so the normalization should be such that at coincident point it is like this. So of course it is easy to see what will be in coincident point. This kernel will be simply sine expand there and cancel these two things, and there will be only square root times the constant. And so I find that the constant should be 1 over pi. Okay, now everything is determined. The only thing that I want to do is to replace the square root of 2n by this rho naught and introduce the variable s, and this is nothing but the following. Rho naught is one of the mean level spacing in the center, and therefore s is just x minus y divided by mean level spacing. So it is an unfolding, in fact. It is in fact an unfolding, the right coordinates, but in this case it is very simple. And so we have finally the correlation kernel, and this kernel is sine divided by sine pi s divided by pi s. So simple as this. And this is for quadratic potential. If the potential is not quadratic, then what I have to do, I have to, the energy will be of course different as a function of n, but the result will be the same as long as I can make such an approximation. Why it will be the same? Because the difference in the n dependence of the energy will be absorbed by this rho naught. So as I said before, this is important because what I told you that there could be strong confinement, and when there is a strong confinement, the density may be not exactly the semicircle, but close to the maximum. It can be made constant. And this constant is exactly this approximation. It doesn't matter what this constant is because it is absorbed in rho naught in the end. It is important that it is constant. But if the confinement potential is not steep, then we know that there will be something like that, and there will be, it is difficult to approximate it by a constant because this approximation is only for the width which is of the order of mean level spacing, and that doesn't make sense. Therefore, such form of the kernel, it will persist as long as I have strong confinement. If I have confinement which is shallow, then this kernel should change. And and now I plug in this kernel into the formula for the density correlation function, and this plot I have already shown to you, and I'm now comparing different approximations. So the most crude approximation is the plasma approximation. These red lines. Then there is an exact solution which is blue. In this case, it is n is 200, and orange is this form which which was obtained using this semi-classical approximation at large N. And you see that it very accurately, already for N equal 200, the difference between the exact and this form is negligible. But if I would have 50, as I said, then there will be a difference. So this is how different approximations work, but you see, this approximation also makes sense, because you see that it is exactly passing through the middle of the parts. And this means the following: this means that this is an envelope. If I average over pulses, suppose pulses are very short, then I can average over pulses, and the average of sine squared will be 1/2. We know that average of sine squared or cosine squared over a pulse is 1/2. And therefore, if I average over such pulses, I will get out of here 1 by 2 pi squared s squared. And this is exactly plasma expression. So this plasma expression is obtained from the exact one by averaging over oscillations. Okay, so now we know how the correlation function looks like for the case beta equal 2, because all what I did, in particular this expression 1 minus k squared, it is valid only for beta equal 2. So what to do if beta is not equal to? So in principle, you see there is some more sophisticated consideration with orthogonal polynomials, which I do not want to bother you. But the thing, the bottom line, the result is the following: that in addition to this 1 minus k squared, there is 2 terms. There is an additional term which for beta equal 1 looks like this, and for beta equal 4 it looks like this. So they are similar, but the difference is in the sign, and the difference is in the limits of integration. So from here you can infer that case beta equal 1 and beta equal 4 somehow are deeply related with each other. But this is a different story. So if I plug it into here, the kernel, which is signed px by px, and integrate, I can get exact expressions for density correlation function in case beta equal 1 and beta equal 4. But at the moment, I don't want to make an exact integration here, because it is expressed in functions like integrated cosine, integrated sine, which tells you little about that. What is more sensible is to plug in the kernel and make an expansion in the inverse S, where S is big. So that can be done by integrating by parts, it is a standard way of getting asymptotics. Simply integrate this thing by parts, and there will be sine and there will be x, and you integrate by parts, and you obtain increasing powers of s in the denominator. So what I did here, I just kept doing that up to the order 1 over s to 4. And this is the result. This is not the density correlation function, but the non-trivial part of it, because if you remember, we said that the density correlation function, which I called R of n, it contains delta function of, if I introduce this s, it contains delta function of s, then it contains 1, and then it contains this y remaining part of s. And these two are trivial, and this one is not. And this is what is shown here. So this is essentially what makes the repulsion and correlation non-trivial. And you see what happens. So there is the first term, which is exactly what we get from the plasma. So the first term comes from the plasma. I mean, it doesn't come from the plasma, but it is the same. And then there is an oscillating term. So since the average of cosine is 0, then it is another word to say that averaging of oscillations, you will get exactly what plasma model does. But now you see what happens. For the unitary case, the oscillating term, it falls down as 1 over s squared at large s. For the orthogonal case, it falls down like 1 over s4. And for the unitary case, there are two terms. The first one is identical to the one in orthogonal, but there is a term which falls down very slowly, like 1 over s, and it has a different period. So how does this term appear? It is clear from this expression. Suppose that s is big. To the first approximation, then I can put here s to infinity, and I have a constant, okay? And then what will be the principal result? The principal result will be the derivative of the kernel. But the kernel is sine pi s divided by pi s. So what I can do? I can differentiate this numerator, or I can differentiate denominator. And when I differentiate numerator, I will get only the factor of pi. Okay? And when I differentiate the denominator, I will get an extra power of s. And when s is large, I don't have to differentiate denominator to get the leading term. So the leading term comes from the differentiating of the sign. If I differentiate sine, I will get cosine, and this is exactly this. It is exactly this cosine, and this integral, as I said, at large s, the leading term is constant, and therefore I have this thing. And here it is not like that, because when s is big, then this integral becomes small. Because when s is infinity, the integral is 0. So then I don't have this leading term in the leading term like 1 over s with the cosine of such period in the orthogonal case. I have it only in the symplectic one. And so you see the symplectic one is sort of abnormal because it has very slow decaying oscillations. So this is how the correlation, essential part, non-trivial part of the correlation looks like. Again, this is plasma, and this is what comes from for instance, orthogonal polynomials. Okay, but then let us look at that from different perspective. We know that Wigner invented not only random matrix theory, he invented many things, and in particular he invented a Wigner crystal. What is Wigner crystal? He asked a question. There is a two-dimensional system. Let us put here electrons, which repel each other via Coulomb interaction. And consider these electrons as a quantum particle. And ask a question. Such electrons will arrange themselves in a crystalline order, or they don't. And that was a discussion question because the dimensionality is not 1, it is 2, but it is still low. And such crystal was called Wigner crystal. Now, then this Wigner crystal was not only present theoretically, it was observed experimentally, and people got Nobel Prize for that. And how they were observed, there was a helium, liquid helium. And what electron did, they, when they sit down here, they produce the well here. So, in this way they stabilize each other, and Coulomb interaction does not make them collapse. And there is also some confining potential made by external charge, and this was realized in the lab. The guy who did it, I have forgotten the name, but once upon a time I was sitting with him in Birmingham. He was a professor in Birmingham, and so I interacted with him a bit when I was in Birmingham. It was a very nice guy. Okay, so then the question, this is a usual Wigner crystal. And then the question is, if you have a one-dimensional system and put particles which interact which do not interact but are fermionic, or they interact like Calogero-Sutherland, what I told you. Then the question is, will the system arrange itself as a crystal? The answer is no, because we know that in one dimension at finite temperature the crystal cannot survive. This is the theorem. But what means crystal or not crystal? Crystal means the following, that if you have density correlation, then if it is a crystal, then you have this correlation function which is oscillating. and not falling. And this is x minus y. It is simply oscillating. And if this is constant, then one can say that there is a long-range crystal order. Okay? But what we have here, we don't have long-range crystal order. We have an oscillation term, but the amplitude falls down. And so we have, instead of that, we have the amplitude which quickly falls down. And this is the maximum that system can do in order to keep some crystal order. So it is, in essence, this is one-dimensional crystal, one-dimensional Wigner crystal. But there is no long-range order, so it is not the normal crystal. But still, in the ground state, there is the falling order which falls down not exponentially, but it falls down as a power law. And this is also remarkable because this is so-called weak order because or short-range order. But the fact is the following: that this short-range order does not have any specific radius at zero temperature, and the decrease is power law. Power law does not have a scale. So this is what happens at zero temperature, because this is a ground state of Kravtsov. Now, if the temperature is finite, then this Kravtsov would have crystal order parameter falling down exponentially, and the temperature would would set the radius of this decay. So when the temperature is zero, there's no radius; it is power law. When the temperature is not zero, then this thing falls down exponentially, but there is some radius that depends on the temperature, and this radius is inversely proportional to the temperature. When temperature is small, the radius is large.
But sorry, in Kravtsov there is no interaction between the electrons, right?
No, there is. In the case beta equal 1 and beta equal 4, there is.
Yes.
In case of beta equal 2, no.
Yes.
But you see, this fact is also reflected here, because if you look at this Kravtsov, then we will see that for unitary ensemble there is no interaction, but they are fermions, therefore they repel each other statistically. Okay. Now, then, when we come to the orthogonal ensemble, then there is a repulsive interaction. So they repel each other stronger than simply statistically. And therefore, this order decreases faster than in this case. So this is the business of repulsion. A change from this to that is the business of interaction. And here the sign of interaction is opposite, and we have slower decay than in this case. So interaction matters here. Okay, so this is how intuitively this picture can be understood. Why different powers? Because interaction changes this power of decay. Okay, so then there is also a useful thing which is called spectral form factor. It is simply the Fourier transform of this R function that I have been talking about. So this, as I said, this R function of S is delta of S plus 1 plus Y of S, which we discussed. Okay, and so this f of s, f of t is the Fourier transform of R of s. Now, what we can say immediately, knowing that it is a Fourier transform. First of all, there is a delta function here. And the Fourier transform of delta function is the coefficient that stands here, 1 or whatever. And it does not fall down with increasing t. And you see this limit where t goes to infinity. It is the business of this delta function. So when t goes to infinity, then this delta function produces unity in case of unity ensemble and orthogonal ensemble, and it produces 2 in case of the symplectic ensemble. Why 2? So 2 means here there is a factor of 2 and not 1. This is because of the Kravtsov degeneracy which I told you about. So each level in the symplectic ensemble is 2 times degenerate, because this is the time reversal symmetry where t squared is equal to -1. And in these two cases, it is equal to +1. So if you have a degeneracy, then how this delta function usually appears? This delta function usually appears, you have delta of E minus En and delta of E minus Em, and sum over N and M. Now, and here, the density correlation function of E prime. Now, when I take N equal to M, then N equal to M, then I have delta function of E minus En, sum over N, and then the delta function of E minus E prime. And this gives you the, after averaging, this gives you the average density, and this gives you this delta function here. Now, when I properly normalize this R, because it is not simply density correlation, but divided by the average, so this factor cancels out, and I have delta function with the coefficient 1. But if I have a degeneracy, then the delta function appears not only when n equal to m. It will appear when this is n and this is m. It will appear a second time. and therefore in front of delta function there is 2 and not 1 in the symplectic case. And therefore this Fourier transform goes approaches to at large time. Why this is useful, this notion? It is useful because it enters the dynamics. So if you study not the level statistics, but dynamics, for instance, you may initially put your particle at a certain site. Since there is no localization, it will escape from this site. And then the question is how much, so you put the particle in a certain site, and then you ask a question, how much initially there is one particle there, and then you ask a question, how much of this unity remains as t increases. So usually what happens is that it decreases, and this function is called return probability or survival probability, how much of this initial unity survives at a time t. Now, this guy is expressed in terms of this f. And also, this is the simplest dynamics that you can think of. But could be more sophisticated dynamics. And in case of Wigner-Dyson, since all the correlation functions are decoupled and factorized in terms of the correlation kernel, everything is expressible in terms of this spectrum from phi. And now, if you take this formula and you plug into here this kernel sine pi x by pi x, one can compute this Fourier transform easily. I'm not going to do it, but everybody of you can do it. And this is the result. The most remarkable one is in case of the unitary ensemble. So there is exactly linear behavior until the time is equal to 1. And then there is the jump in the first derivative and the spectrum form factor becomes exactly 1. So here the point t equal 1 is the point of singularity, and the first derivative has a jump here. Why it happens is easy to understand, because here there is an oscillating term. And when I do the Fourier transform, so what I have this oscillating term, which is e to the 2 pi I s, also with the other term, and then there is e 2 pi I s times t in the Fourier transform. So this one. And now when these two things exactly cancel each other, then I have singularity. So 2 pi I s equal to 2 pi I s times t, and then I have t equal 1 as a point where there is a singularity. this thing is not only valid for the unitary ensemble, it is also valid for any other ensemble. Because this argument is common. So you have these oscillations with 2 pi everywhere, and therefore you have this singularity in any ensemble, but here you have a jump in the first derivative, and here you have a jump only in the second derivative, which on this plot you don't see. Jump in the second derivative, why? Because there are two different forms at t smaller than 1 and at t larger than 1. And these two forms match each other smoothly, and also smoothly in the first derivative, but not smoothly in the second derivative. Because if on the left or on the right you have a function, non-trivial function, and then you have just constant, you cannot do it smoothly, because some derivative will have a jump. Okay, so, but then there is also an interesting feature in the symplectic ensemble, because of this term, of this anomalous term. It has not 2 pi s, but pi s. And if I write here not 2 pi s, but pi s, then I will have not t equal 1, but 2t equal 1. So t equal 1/2. So there will be a singularity at t equal 1/2 because of this term. And it will be very strong because these oscillations fall down very slowly. And this is what happens. Here there is a logarithmic divergence. So in symplectic ensemble shows anomaly in dynamics. Because here you don't even see that there is a singularity. Here you see. Here you also don't see that there is a singularity at 1. But you see a strong singularity at 1/2. Okay. So now a bit more complicated stuff with different physics. I not derived, but I could have derived this expression for asymptotic behavior at large s. Now, if I look carefully at this expression, then I can notice that both oscillating part and non-oscillating part can be expressed in terms of one single function. And this single function is like this. It is simply to rewrite what I have shown before. But important is that there is one single function that controls the amplitude of non-oscillating part, the amplitude of oscillation with 2 pi, and the amplitude of oscillation with pi in any of these ensembles, in the unitary, orthogonal, and symplectic. So there is some unexpected simplicity that there is only one function that controls all these amplitudes. Not only that, there is a certain coefficients here. Here coefficient 2, here coefficient 1/2, here coefficient 1, which are also not accidental, as we will see. So what does it all mean? It means the following, that this form was derived, if you wish, from Kaluza-Sutherland. It can be derived from Kaluza-Sutherland. And this is the fermionic system with interaction or without interaction. So think of it as something which was derived from the ground state of some fermionic system. But this function, which appears here, it is a function typical of bosonic system. And I will explain it in more details. In particular, this function is expressed in terms of the correlation function of some field phi at coincident times. So there is 1 plus 1 space, so one-dimensional space plus time, which is usually in quantum mechanics, 1 plus 1 space. And this function can be obtained as essentially the Green function at coincident times, but not coincident space, of the from the action, from the functional of bosonic action. Moreover, it is quadratic in this phi, and since it is quadratic, they are non-interacting bosons. So what we have a remarkable situation that generically interacting fermions can be expressed in 1D, can be expressed in terms of 1D bosons. So this is so-called bosonization. So you may think of this formula as some correlation function of interacting fermions, and you may think of the same correlation function as something that follows from non-interacting bosons. And this was actually maybe the most significant, at least among few most significant developments in condensed matter, or not only in condensed matter physics, when people realized that in 1 dimensions, fermions and bosons are two different but dual descriptions of one and the same thing. Moreover, fermions may interact, and this is a difficult problem to treat interacting particles. But bosons, which are equivalent to those fermions, are non-interacting. And therefore, a lot of problems with interacting fermions were solved in this way, in one dimension. So, as I told you last time, so first people tried to do diagrammatic expansion, Feynman diagrams, sophisticated set of diagrams, and this was a nightmare. But when it was realized that it is simply an attempt to describe bosons having diagrammatic technique for fermions, it is simply, two different, very distant descriptions, and that's why using the fermion description in case of interacting fermions was extremely not economic way of getting the results. And the boson-sign non-interacting result comes immediately. So, before I finish, a few explanations. So why in one dimensions fermion may be equivalent to bosons? The thing is the following, that what makes fermions? This is the following, that you can make an excitation above the Fermi sea, which is a quasi-particle which behaves to the first approximation like a free fermion. But in addition to single particle excitations, you can make what is called collective excitations. And collective excitations is the following. Suppose you have particles in one dimension. Then what you can do, you can vary the distance between these particles. You can vary the density. So this here density is a bit smaller, here density is a bit higher. And so you can vary the density. And what is varying the density? This is sound. Because what is sound? In air, longitudinal sound. It is simply variation of the density.
Yes.
And in 1D, such excitations are present not only in 1D, such excitations are present also in higher dimensions. So there are plasma modes in let's say, in 3 dimensions. But what we know that the sound and plasma collective modes, they are bosons. They are not fermions. And single particle excitations are fermions. So if you can take one particle and move it, let's say, separately from all the others, that will be a single particle excitation. But you live in 1D, you cannot jump over the head of the others. And because you cannot jump over the head of the others, what remains are only the sound. In 2D and 3D, you can do it. You can circumvent. So, for instance, even in 2D, suppose you have particle here and you want to arrive here. So you do not have to push all these particles. You can go this way and arrive where you want. In 1D you cannot do it. And this is, in fact, the same phenomenon is why in the street with only one lane, you have the traffic jam. Why? Because you cannot jump over. If you have two lanes, you can do it like this. In one lane, you cannot. And therefore, if you are driving in one lane, you are driving with the velocity of the slowest vehicle. But if the path is long, then the probability to find a slow vehicle is going to 1. And that's why traffic jams. And here, if we return to this interacting fermions, the impossibility of jumping and having the parallel shortcut leads to the fact that that all excitations are only of bosonic nature. And that can be shown formally. That can be shown formally for those who are interested in the details of that. There is a beautiful book by Cvelik and Gogolin and Nersesyan. This is a book which collected zillions of. So I would recommend this book for those who want to know more about this formal part of the story. But there is even, I would not say better, but even more accessible book on the same matter by T.V. Giamarchi. This book is, is almost like science fiction. So you do not have to have a stress, mental stress, because he manages to explain things in so simple way that you become happy, but then you cannot calculate anything. But if you want to be a little less happy, but to calculate something, you should go to the book by Cvelik and Nersesyan and Gogolin. Okay, so I'm almost finished. So what I wanted to show here, I wanted to show that why fermions may behave like bosons. And then the other thing is how to describe it. Suppose we have a fermions, and there is a Fermi C here. Then you know that there are 2 points, K Fermi and minus K Fermi, which depend on the density of particles, and if you are in one dimension, the particle with plus K Fermi, it goes right, and the particle with minus K Fermi goes left. And so you can separate particles by right movers and left movers. Then, if there is no density fluctuation, then your wave function is simply a combination of the right moving wave and the left moving wave. But when there is a density fluctuation, which are quantum fluctuation, you put here not just numbers, you put here operators. And these operators describe the density variation. So there is one operator that stands here, and the other which stands in front of the left movers. And you introduce 2 fields. One is phi of right movers and the other is phi of left movers. You know, returning to our, from this condensed matter analogy, returning to our problem, you know that there is 2 pi s and there is pi s. This means that your Fermi momentum formally is 2 pi. Momentum is sorry, just a moment. If I write it in this way, okay, so then the Fermi momentum is, we know that in this case, in these two cases, there are only 2 pi. And so the Fermi momentum is 2 pi. And in this case, there is both 2 pi and pi. So there are 2 types of oscillations. And this is a situation which in condensed matter, so simply it doesn't appear, but I identify this K Fermi comparing these oscillation terms. X will be S, and the frequency here will be either 2 pi or pi. So here I didn't write it, so it should be 2 pi and pi. Yeah, and this is the bosonic operator that takes account of the density correlation. And then one has to write what is the density. And the density usually is psi dagger times psi. So if I do so, then what I have, I'm right here. I'm right here because in the density, so what I considered there was the density. And in the density is a bilinear operator. So if I have here pi, then in the density I will have 2 pi. So it is correct. So pi or pi over 2. And usually the density is like this. And so you substitute this operator here, and you obtain the density operator in terms of this phi. And but the point is that this is a long-range theory. So it is a long-range theory in the sense that I can so my dispersion relation, suppose, is like this. When I give a number which is a momentum, so I make I say that this is plus K Fermi and this is minus K Fermi. But in fact, and then I can define the velocity, and the velocity, if it would be a linear dispersion, then the velocity would be K Fermi times m, and it would be just constant. But in fact, there is some curvature here, and all this theory which I'm going to present, it is neglecting this curvature. It is only it pretending that the dispersion relationship is just linear. But in fact, if you have a process which involves large momentum transfer, so you will be feeling that here there is a curvature. So here you may say that the curvature is, you may neglect the curvature. But if you have large momentum transfer, then you know that here there is a parabola and not just a conic point. And this is the difficulty of this theory. It should be very carefully considered this this situation, and I cannot describe it in more detail, so you can only read the books which I cited. But what appears because of the difficulty that there is this conic point somewhere, if I make these things pretend that they are linear, then there will be some anomaly, and in addition to that, there could be other terms appearing here. And then you will have a possibility of different oscillations. So oscillations of cosine 2 pi s and cosine of pi s of two different things. This is because if there would be only this term, I would have a definite oscillations and the frequency of oscillations. And this is the case for the unitary and orthogonal ensemble. But in the symplectic ensemble, this coefficient, there are two terms which make contribution, and in fact, to know how many terms, how many frequencies there will be in the formulas like this, how many frequencies, it depends. It depends on the initial problem. So there is the Kalogero-Sutherland problem, and this problem has, as you know, some singularity because it is inverse square interaction. And in principle, this problem has exact solution, and from that exact solution, you can find how many terms, how many frequencies will appear. But you cannot say, having only the long-range theory, which ignores this singularity, you cannot say how many frequencies, how many coefficients here are non-zero. So in principle, it could be many. So it could be many frequencies. But the Kalogero-Sutherland is the simplest possible model of that type. It has at most two frequencies. At most two coefficients are non-zero, all others are zero. But this can be only inferred from the full solution of the Kalogero-Sutherland. So if we know this full solution of Kalogero-Sutherland, we know how many terms with non-zero coefficients, and we know those coefficients, its value. And in this case, you simply can take this from the solution of the this can be thought of as the full solution of the Kalogero-Sutherland, and from this solution, I know, for instance, that here there is only one frequency. Here there is also only one frequency, and here there are two frequencies, and that coefficients here is 1/2, and here is also 1/2. So this the value of these coefficients here can be obtained only from the full solution, not from this long-range theory which I'm going to present. And then if you say that you know from somewhere all these coefficients and how many of them are non-zero, for our theory it is only 2 non-zero at most, then I can plug this thing to here and obtain the density minus the average density, and as a function of this field, of this bosonic field. This is simply the algebra. So you put this stuff to here and get this this stuff here. So yeah. And we will be working with that. So you see, I told you that this the first hint that we deal with something which allows a bosonic description. It was that this function, in terms of which we can express everything, that this function is a correlation function of the free bosons. And this, you see, it is a correlation function of e to I phi, e to I phi. And why e to I phi? It is because it appears here. So this this field phi enters as enters in the exponent, and therefore it appears naturally that you have to deal with correlation function of e to I phi, and then everything can be calculated, and this will be done next time. So I'm sorry about this crash course of what is called Latin geometry, but my of course I cannot explain all the details over there, but I can possibly give you some flavor of what this theory is about, and there are beautiful books. So if someone is interested in that, so in this way. It is possible to consider also superconductivity. It is possible to consider even dirty superconductivity in one-dimensional system, and much of work has been done, and therefore it is a very specific thing, because, as I said, there are no one particle excitation. And this is the special property of one-dimensional systems. Okay, so take it as it is. So you know, when I'm giving you a crash course, I can only give a flavor. I cannot give you, you know, many details. I answer all the questions. But something I taught here, and I will be using that. Why I went for that? Because first of all, it is a nice analogy, but not only. You see, this is the action of the free bosons. We will see that those correlations are obtained as a theory of free bosons. Okay? But in this, but those correlations are ground state of the system of free bosons. And when I write the action, then we know how to take into account temperature. You have to put here the imaginary time integration up to 1 over temperature. So if temperature is 0, this is integration over semi-axis. If temperature is not 0, this semi-axis is closed to some ring with the circumference equal 1 over t. And then those who studied the green book by Abrikosov, Garkov, Zanashinsky, we know how to deal with that. You have to introduce Matsubaru frequency. So to deal with 3 bosons at finite temperature is a simple generalization of this problem. But what we know that Wigner-Dyson corresponds to 0 temperature. But we can make generalization to the finite temperature. And the question is, will this generalized theory correspond to some other random matrix ensemble or not? So the answer is that it does. And it corresponds to the power law-banded matrices. So the power law-banded matrices appears to describe by the same theory, but at finite temperature. And what means this temperature in terms of parameters of this model? And I tell you now what is it. It's quite a material. Yeah. You see, this is a power law-banded matrix, right? Now, here there are 2 parameters, A and B. A is a parameter that controls the phase. So if A is greater than 1, we are in an insulator. If A is smaller than 1, we are in the metal. If A is equal to 1, we are in a multifractal state, which is essentially the critical state like in the Anderson model. But, then if I set A equal 1, what remains is the parameter B. And it appears that the temperature in those bosonic theory is 1 over 4b. So if B is large, then this matrix, if B is large, then I can neglect this thing and I have the variance equal to 1, and this is Wigner-Dyson. So if B is large, I have 0 temperature, and this is Wigner-Dyson. If B is very small, I am approaching Poisson, and this corresponds to infinite temperature regime in this bosonic theory. So it appears that I considered Wigner-Dyson. I represented it as a bosonic theory, and then I generalized this theory by finite temperature. And then it appears that in the random matrix theory, the finite temperature means the lack of basis rotation invariance, because this matrix is not basis rotation invariant. And at zero temperature, and then, as I said, the finite temperature will generate some scale. The correlations will fall down not as a power law but as exponent, and this exponent will have a scale, and this scale will be an inverse temperature. So things like that. Don't be confused, because in the classical analogy, the temperature is beta. The temperature is symmetry parameter. In the quantum analogy, if I in a bosonic analogy, if I put the temperature, not only in the bosonic, in fermionic too, if I put the temperature, I go beyond Wigner dice. I will have Pavlov band matrices which are not invariant under rotation. So, you know, this game of different descriptions, they indeed opens up some possibility of generalizing, of finding a nice description for this power law matrices, for instance. Okay, sorry for complexity, but this is how world works. Okay, for today is all. So next time I go on and compute this correlation function of bosonic field and show that indeed this bosonic description works and reproduces this result, which can also be obtained from fermionic description. But bosonic description is much simpler because it is free bosons. To solve Calogero-Sutherland is a big deal. It is more complicated than to solve Wigner dice. And to solve the bosonic theory is less complicated than Wigner dice. And this is what I want to say, that in order to get, for instance, these formulas for Wigner dice, which I never have shown for you, in order to obtain these two terms, I have to work. It is, you know, tens of pages in the book of on random matrix theory. But to compute the correlation function of three bosons